All right, let's dive into one of the biggest puzzles in manufacturing, machinability. We're going to put together a lecture note on the science of cutting materials that are specifically designed not to be cut. Things like jet engine parts or super hardened steels. So how in the world do you shape something that's built to resist being shaped? Well, that's exactly what we're going to figure out.
So, have you ever wondered why cutting a superalloy, like the kind you'd find in a rocket engine, is so much tougher than cutting a simple piece of steel? It really all boils down to one single primary enemy: heat. The friction right at the tip of the cutting tool creates an incredible amount of heat, and winning the battle against that heat is the name of the game.
Okay, first things first, let's get a key term on the table: machinability. Now, this isn't just about whether you can cut something, it's about how well you can do it. Are you getting a nice, clean, smooth surface at the end? And critically, are you doing it without absolutely destroying your cutting tools in the process? That's what machinability is really all about. So here's our game plan. First, we're going to dig into that core challenge I mentioned, heat. Then we'll look at how the solutions have evolved, from the old-school conventional methods to something called MQL. After that, we're going to the extreme, into the cryogenic frontier. And finally, we'll check out the data and see what kind of impact all this technology really makes.
Right, let's start with our main villain, heat. Every single time a tool slices into metal, there's this intense, microscopic battle happening right at the cutting edge, and it's a battle completely defined by friction and soaring temperatures.
And when I say intense, I mean it. The heat in that tiny cutting zone can spike to over 1,000 degrees Celsius. At temperatures that high, even the hardened steel of the cutting tool starts to soften and wear down incredibly fast. This not only ruins your tool, but it also gives you a rough finish and can actually damage the properties of the material you're trying to shape.
So if heat is the problem, how do we fight back? Well, let's take a look at the evolution of cooling solutions, starting with the traditional way of doing things and moving into some much smarter, more advanced methods. On one side, you have the classic approach, flood cooling. This is exactly what it sounds like. You're just drowning the cutting area in a high volume of coolant. It works okay for basic stuff, but it's messy, it's expensive to dispose of, and honestly, it's just not enough for tough superalloys. On the other side, we have the modern evolution, MQL, or minimum quantity lubrication. Instead of a flood, MQL uses a super precise, targeted mist of oil and air aimed right where you need it. It's a less is more philosophy that creates this ultra-thin lubricating film that just slashes the friction.
But what if you can make that mist even more powerful? Well, that's where things get really interesting. Researchers started asking, hey, what would happen if we mixed tiny microscopic particles, nanoparticles, into that MQL mist? And the result, my friends, was a total game changer. So how does this magic actually work? It's pretty clever. You start with the same oil and air mist from regular MQL, but then you suspend these nanoparticles inside it. When this supercharged mist hits that hot cutting zone, the nanoparticles do two amazing things at once. First, they act like billions of tiny, microscopic ball bearings, which cuts down friction. And second, they're great at conducting heat, so they literally pull heat away from the tool much more efficiently than the oil could on its own.
And the results? They speak for themselves. Get this. One recent study found that when machining a very common titanium alloy, just adding these nanoparticles to the MQL mist dropped the cutting temperature by over 17%. That is a huge difference, and it leads directly to a tool that lasts longer and a part that's made better.
But for the absolute toughest materials out there, we're talking gamma titanium aluminides used in the hottest parts of a jet engine, even nano MQL might not be enough. For those, we have to go to the next level. We have to get extreme. Welcome to the cryogenic frontier.
Yeah, we're not just cooling things down anymore. We are flash freezing the cutting zone. The go-to coolant here is liquid nitrogen, or LN2, which exists at a frankly mind-boggling minus 196 degrees Celsius. We are literally fighting extreme heat with extreme cold. And the benefits here are just profound. This intense cold yanks heat out of the tool and the part incredibly fast. It stops the kind of tool wear that only happens at high temperatures, like when atoms from the material actually start to fuse to the tool. It also prevents little bits of metal from sticking to the tool's edge, which gives you a much cleaner cut and a way better surface finish, something that is absolutely non-negotiable for critical aerospace parts.
And of course, engineers being engineers, they're already pushing things even further. The absolute cutting-edge, state-of-the-art method right now is hybrid cooling.
This combines the insane heat-sinking power of cryogenics with the slick, friction-reducing lubrication of MQL. You get the best of both worlds, and research is showing this is the top-tier approach for the toughest materials, like titanium alloys.
Okay, so we've gone through a whole bunch of different cooling techniques, but what does this all mean in the real world? Let's take a look at how these strategies actually translate to performance, because that's what really matters at the end of the day.
This chart tells a really clear story. If you try to machine dry with zero coolant, your tool life is, well, it's our baseline. Not great. Switch on the MQL, and you see a really significant jump in how long your tool lasts, because you're managing that friction and heat. But then when you jump to cryogenic or a hybrid system, that's where you get the maximum possible tool life. You're just aggressively tackling the root cause of the failure, which is heat. And longer tool life means lower costs and getting more work done. It's that simple.
So really, the big takeaway is that there is a right tool for every single job. This little dashboard right here, this is the ultimate lecture note. For basic stuff like aluminum, your conventional flood cooling is probably fine. Stepping up to titaniums or tough mold steels, MQL is a fantastic, sustainable choice. Need that extra performance boost for a perfect finish? Nano MQL is your answer. And for the absolute peak predators of the material world, the aerospace superalloys, you bring out the big guns, cryogenic cooling.
And this quote from the source material just sums it all up perfectly. It's not about finding one magic bullet solution that works for everything. It's about building a holistic strategy. You have to understand your material, know what you want the final part to look like, and then choose the right cooling and lubrication technique to get the job done.
And that leaves us with one last big thought. We are constantly engineering new materials that are stronger, lighter, and can handle more heat than ever before. So the question for the future is, as we create these incredible materials of tomorrow, what will the next revolution in cooling technology even look like? What's going to come after cryogenics?